So let's look at a quick example. Here we have a 6-sequence string. Computer Science 89.32 is a fun class. If we decide to delimit by the spaces here, we can then take each of these tokens and generate an embedding for them. So here are each of the individual token embeddings, and then we can concatenate them together to essentially represent the entire sequence. So this would be an S by D matrix where S is our sequence length, and then this D here is our embedding dimension. Then at every transformer block, we would do a matrix multiplication with the Q, K, and V matrices that all have an S by D dimension. So within the attention mechanism, we would do Q by K transposed, which is the most computationally expensive part because Q by K transposed generates an S by S matrix. You can prove this because Q is S by D, K is S by D, you transpose K, that becomes D by S, and then it's S by D times D by S, which becomes S by S. And the memory efficiency is theta of S squared. So it'll always scale quadratically with respect to the sequence length. Now, for something that's 6 tokens long, that's not too bad, but if you gave it an entire corpus, like an essay or a textbook, your S could be upwards of 100,000 or even 1 million, which means that this is a lot of VRAM being used. And more importantly, you don't necessarily need every single token to generate a good output. For example, if you read Macbeth, let's say, you might not know what's on page 232 exactly word for word, but you still have a good high-level understanding of Macbeth as a literary piece, and you know who the main characters are and the plot and so on. And so what Mamba tries to do is figure out which parts of an input, which here I model as sort of like a signal, are important to remember. In a transformer, we take every part of the signal and transcribe it perfectly. Every single token is perfectly present within that S by D matrix. But in Mamba, the selective state space mechanism decides which parts of the signal it needs to preserve. So right here, where we have this kind of undulation, we decide in Mamba not to keep it. But here, where there's this sort of peak, Mamba decides to preserve perfectly in this example. And that's because the selective state space tries to figure out what parts of the original signal do I actually need in order to make a good output. If we look at the actual differential equation being used to model Mamba, which is what the Mamba block tries to represent, it shows H prime sub t, which is how does the hidden state change with respect to time, being equal to some matrix A, which is a learnable parameter, multiplied by the current hidden state. Here, we can think about A as what parts of the current hidden state do I need to forget? That's then combined with B, which is another learnable matrix, multiplied by the current input. Here, I show it as a signal. And what B is supposed to show here is what part of the current input signal, x sub t, do I need to remember. Then we create some output here, y sub t, which again I show as a signal, and that's equivalent to some learnable parameter matrix C multiplied by the recomputed hidden state. And C is supposed to represent what parts of the hidden state do I need to extract in order to generate a good output. And Mamba does a really good job, and we'll get to performance in a bit, but a few other notes. The first one is that Mamba does some hardware tricks in order to speed up its effectiveness. So this hidden state is sort of remembered between every time step. So you can just keep it directly on the SRAM on chip instead of having it on the HBM and constantly reloading it back and forth. And also, Mamba can be represented as this singular block. So we do an upward projection, go through a convolution, multiply by a nonlinearity, then push it through a structured state machine, and then combine it with our skip connection before down projecting it. And what this means is we can just keep stacking these blocks on top of each other to make a very large Mamba model, which means it's agnostic to the input type. So here, if we look at some of the results, we can sort of see that Mamba's done exceptionally well. In fact, compared to other sorts of RNN type models that Mamba technically is trying to be an RNN by doing O of 1 inference and only relying on the hidden state, it doesn't lose any accuracy. This is where Mamba is. It stays at almost 100% accuracy even as the sequence length grows to 10 to the 6th, whereas H3 or Hungry Hippos, Hyena, MHA all drop off. We can also see it's one of the first models to beat Transformer++, which is right here, and right here in terms of perplexity, which is very impressive and something people have been trying to do ever since Transformers came out. And we can also see the scan versus convolution and attention time compared to Flash Attention 2, which is a state-of-art implementation of attention. And here is the scan and their scan. And this is the throughput, which is just exceptional.